All right. Hi, everyone. My name's Casey. I just barely graduated from the University of Hawaii Institute for Astronomy, working with Dan Huber and Lauren Weiss. And I will be applying for postdocs this fall. That graphics got a little cut off. So if you have interest in what I'm talking about, feel free to come up to me and chat after. So the field of exoplanets and myself have something in common. We were both born in 1995 with the discovery of 51 Pegasi b. That means that we're both rapidly approaching our 30th birthdays. And the field of exoplanets and I have another thing in common, which is we've spent an extremely large portion of our lives wondering about our place in the universe, if the Earth is unique in our galaxy, in its composition, its ability to host life, or if it's in fact a pretty average rocky world. And one of the most important aspects to characterize when we're assessing the habitability or potential Earth-likeness of an exoplanet is its composition. So planets can be assumed to be composed of four primary components: an iron core, a rocky mantle, an ocean or a water layer, and a gaseous envelope composed of hydrogen and helium. For planets smaller than 1.5 times the size of the Earth on short or ultra-short period orbits, we can assume that they are too hot and too low mass to retain a hydrogen or helium envelope. And in fact, we can also assume that they don't contain a significant water fraction either. Therefore, we can assume that most planets smaller than 1.5 times the size of the Earth are primarily composed of just iron and rock. And we can estimate this ratio of iron to rock for rocky planets using mass and radius measurements. So this is where a planet would fall in terms of radius at a given mass if it has an Earth-like composition of roughly 30% iron, 70% rocky mantle. A planet with no iron core, just silicate rock, would sit above the Earth as the least dense possible rocky planet. And any planets sitting above this line on a mass radius diagram are likely host a gaseous envelope, either made of hydrogen and helium, like a subneptune, or of high mean molecular weight species. And planets composed entirely of iron would fall down here as the most dense rocky planet possible. Any planets below this line would need to be more dense than 100% compressed iron, and that's probably a measurement error. So the shaded region represents the expected diversity of composition for rocky planets if they indeed span that full range of 0% iron to 100% iron. And when we plot the masses and radii for planets less than 1.8 Earth radii with well-characterized masses, we can see that planets not only span this full range, but that several appear to be less dense than rock and more dense than iron. So in order to test whether or not this diversity of compositions is real or a product of poor measurements, we conducted a 3-year campaign to collect high cadence and high precision radial velocities spanning planets that represent a wide diversity of apparent compositions. So we used both Maroon X on Gemini and KPF on Keck. We collected hundreds of RVs on these planets, focusing on high cadence RVs in order to eliminate stellar variability or instrument instability, given that these are both relatively new instruments. We also utilized high-res on Keck as well, primarily as a test of Maroon X's stability early on, and also as a way of extending RV baselines for planets that already had high-res observations historically. This allows us to better account for additional planets in the system or any other long-term trends. So another thing that we did was we conducted a homogeneous analysis of the host stars in our sample. And so we measured stellar masses and radii using isochrones. And this allowed us to update the radii for each planet in addition to the mass, and to make sure that we were using as homogeneous a sample as possible. So the first planet that was in our survey is TOI 561b. This is an ultra-hot rocky planet orbiting a star in the galactic thick disk. And when we set out to characterize this planet, there was not one mass measurement in the literature, but two. One of these, measured using high-res, suggested a relatively iron core, but still distinctly rocky composition. The other mass, measured using HARP, suggested that there had to be a substantial gaseous envelope, likely composed of high mean molecular weight species, which is really unusual for a planet of this size. So using an independent third spectrograph, Maroon X, we measured the mass of TOI 561b and found that it sits right on this boundary of being a rocky planet and those with gaseous envelopes. In order to break this degeneracy, we are eagerly awaiting phase curve measurements from JWST to determine if this planet shows evidence of an atmosphere or gaseous envelope as measured through heat redistribution in the phase curve. And our analysis of this planet was already published separately in 2023, so feel free to check it out if you're interested and want to read more. But I only have 11 minutes, so I have to talk about other planets. So the next one in our survey was Kepler 100b. This is a planet that was thought to have an extremely high core mass fraction and nearly 100% iron. But after following up this planet with high cadence RVs from Maroon X, we find that it has a much lower mass than previously thought, and therefore an iron fraction that's more consistent with the Earth. The next planet in our survey is Kepler 10, first rocky planet discovered, also a thick disk star. And we found that after following it up, very little change in the mass and radius of this planet, just to be expected. And the next planet in our sample is Kepler 407. This planet orbits a star of high metallicity, 0.4 dex. But most publications had a very difficult time measuring a mass for this planet, and it had a very large fractional uncertainty. But after extremely high cadence RVs from KPF, we were able to pinpoint the mass of this planet more precisely, and it shows that it's right along this Earth-like composition line. Next up, we have TOI 1444, a very average Earth-like planet, which after follow-up still appears to be a very average Earth-like planet. But then we looked at another one of these famous super Mercury type planets, HD 93963AB. And after high cadence follow-up with KPF and a new value of RPR star from Polanski et al. 2024, we find that this planet is no longer consistent with being a super Mercury or even having a remotely Mercury-like composition, and it is instead way more consistent with an Earth-like planet composition. In addition to all of these planets that we carefully selected to test the diversity of planet compositions, we had the opportunity to confirm a planet, TOI 1011, which is a roughly 1.5 Earth radii planet detected in the TESS, Spock, and Quicklook pipelines. And with RV follow-up from Maroon X and TESS photometry, we measured masses and radii for this planet that, show that it is a very Earth-like planet. Yeah, right? And so I'm sure you picked up on our big picture conclusion by this point, but after high precision, high cadence RV follow-up, we found that every single planet in our survey moved closer to the composition of the Earth than its previous literature values suggested, with the exception of TOI 561b, but it's closer to an Earth-like composition than the HARPS measurement was. And so to quantify this, we compute the fractional root mean square error between each point in this Earth-like planet composition line. And we find that after recharacterization, this error gets cut in half, meaning it is a much better fit to our new data points than it was to the old data points. And in particular, the most dramatic change is in the compositions of these is from these super Mercury planets, becoming much more Earth-like. And this is in harmony with other updated RV mass measurements from others. It's in harmony with mass measurements that I've previously published using Gaussian process to model the stellar activity. And it's in harmony with planet formation theory that has been telling us for a long time that forming planets larger than the Earth that are enriched above 50% in iron is actually very challenging to do. And we don't expect to see many out in the wild. However, the compositions of these planets did not fall out of a coconut tree, and they exist in the context of the protostellar nebula that came before them. And so we can compare the composition of these planets to that of their host stars. So planet composition is core mass fraction on the y-axis, and the equivalent value from stellar abundances is on the x. And this dotted line represents the 1-to-1 line if each planet inherited the same ratio of iron and magnesium as its host star. And we see the solar system planets with Venus, Earth, and Mars in the middle, and Mercury at top. These updated planet masses that we just discussed are shown along with a sample of homogeneously characterized planets from a recently submitted paper, mine in gray. And here in pink is our updated linear orthogonal distance regression fit, which shows a slope of 2. So this is steeper than a 1-to-1 slope, but consistent within 1 standard deviation and very similar. And in particular, it's in stark contrast to the rather famous fit from Adebekian et al. 2021, which showed a very steep and statistically significant correlation between the relationship of planet and host star iron to magnesium abundances. And much of this change is driven by the inclusion of these super Mercuries that we find don't really hold up after high precision RV characterization. This paper will be submitted this month and dropping on an archive near you soon, so look out. And I'm sure many folks in this room are co-authors on this paper, since many people here, I presume, worked on KPF, thank you for your hard work. Your RVs are amazing. Also, email me back if you're on the paper. I would love to get this submitted. So to conclude, we investigated the diversity of Earth-sized planet compositions using high cadence RVs from RUNEX and KPF. And we found that in some ways, this diversity of planet compositions is less than we previously thought. We found that most planets tend to have Earth-like compositions, and we've in particular found fewer supermercuries than previously thought. On the other hand, 2I561b still tells us that low-density planets that are roughly the size of the Earth are possible, and that not all planets less than 1.5 Earth radii can be assumed to be rocky, and so we should keep this in mind when assuming compositions for small planets. So with that, I will take any questions. Thank you.